Thank you, everybody, for attending this this workshop. This is the second part of the workshop we held yesterday with Professor Allard and Professor Matt Santamoris and myself, and it was chaired by Professor Fabrizio from Politecnico di Torino. I think I have the control. Yes. So this workshop is dedicated to the energy efficiency in the building and the construction sector. So we dealt yesterday with different topic related to heat island storage and indoor air quality. And today we are welcoming two other professors, Professor Hilcio Holland as keynote speaker, and also Professor Enrico Fabrizio from Italy. Professor Orland is from Brazil, and Professor Fabrizio Enrico Fabrizio is from Italy. So I will start by just introducing Professor Orland, who is from the Polytechnical School of Federal University of Rio de Janeiro in Brazil. He has several degrees from this university in the field of mechanical engineering, and also he has a PhD degree in the same field from the North Carolina State University. And as an experience, he worked and joined the Department of Mechanical Engineering of his university, the Federal University of Rio de Janeiro. He also was the head of the department during 2 years, from 2006 and 2007. And his research area of interests includes the solution of inverse heat and mass transfer problems. He participated a lot for contributing to book writing as for books, and also more than 150 papers in major journals. So he is also a member of the Scientific Council of the International Center of Heat and Mass Transfer, and a delegate in the Assembly of International Heat Transfer Conference. He served as associate editor of the Journal of Heat Transfer Engineering, Inverse Problem in Science and Engineering. And today he selected to propose the topic of his presentation is selection and calibration of models of water absorption in porous building materials. Professor Orland, you have the floor. Thank you.
Thank you very much, Professor Mohamed Mankibi, for the very kind introduction. I'm going to start sharing my screen here. Please let me know if it works.
Yeah, perfect.
Okay. So again, thank you very much. Okay. So again, thank you very much. And let me greet you and all the participants with a good morning from Rio de Janeiro. It's about 8:30 here. Although we had a lot of rain during November, today it's a sunny day and the temperature is around 25 centigrades. Before I start, I would like to say that it's a great honor for me to make this presentation, and I would like especially to thank the conference organizers for the invitation. In particular, Professor Mohamed Garoun, Professor Najim Alahous, Dr. Zaid Romani, and Professor Youssef Vaz. I also congratulate them for the very nice and extremely well organized conference amid the pandemic. And this work, it's actually a very specific topic, and, but it's a collaboration with Julien Berger and Thibaut Collinard and Bruno Loyola. Julien is from Université de La Rochelle, Thibault from Université de Bretagne Sud, and Bruna Loyola, she's a faculty member of the Military Institute of Engineering in Brazil. Let me tell you up front that my name is the last one in the list of authors, not because I was the head of this research, but really because I was the one that who did the list of work. This work has been published in the Journal of Wood Science and Technology. It has just come out. And this is the summary of my presentation. I'm going to make a brief introduction, the motivation and objective, talk about the experiment, the mathematical models, the approximate Bayesian computation algorithm for simultaneous model selection, model calibration, results and discussions, and then the conclusions. So, human curiosity about natural phenomena has always played a fundamental role for the advancement of science. In fact, the search for the truth, what is called the truth, has passed through the analysis of empirical evidences. And as natural phenomena were better comprehended, attempts have been made for the theoretical model. And here, quote Fourier, who wrote in his treatise that the profound study of nature is the most fruitful source for mathematical discoveries. Modeling of natural phenomena generally involves conservation laws and constitutive equations based on empirical results. Moreover, models are based on hypotheses, which directly affect the mathematical formulation of the problem in terms of the number of dimensions, time dependence, scales, linearity, model parameters, etc. In general, more complex models are usually proposed as knowledge is built up with the advancement of science. But commonly, these models are over-parameterized and not necessarily more accurate than simpler ones. Thus, the principle of parsimony must be pursued to obtain simple models with a small number of parameters which accurately represent the phenomena under analysis. So besides situations where the models can be written based on conservation principles and constitutive equations, there are many others that strongly rely on empirical evidences, including experimental data or a priori knowledge about, like a personal own experience. For example, such is usually the case in biology or economics. And more recently, data-driven models based on artificial intelligence tools have been gaining great interest of the scientific community, but such meta-models will not be considered here. Parameters appear in any mathematical model of natural phenomena, from the simplest to the most complex ones. The estimation of parameters or functions appearing in mathematical formulations of problems in nature by using measurements of some response of the system and the calculated corresponding dependent variable of the model is an inverse problem. In this work, we consider the solution of inverse problems within the Bayesian framework of statistics, where credit is also given to previous beliefs about the unknowns, in addition to the information provided by the measured data. Such previous information can even be qualitative, but needs to be represented in terms of a probability distribution function. And these prior distributions, they promote regularization of the solution of the inverse problem, but unfortunately, they induce bias. The term Bayesian is commonly used to refer to techniques for the solution of inverse problems that fall within the framework of statistics developed by the Presbyterian minister, Thomas Bayes. Such framework was actually established after Bayes' death, when his friend Richard Price, in this paper, he published Bayes' results. On the other hand, it's attributed to Laplace the mathematical formulation that is known today as Bayes' theorem. The solution of inverse problems within the Bayesian framework of statistics relies on inference of the posterior distribution of the parameters. In this context, Bayes' theorem relates the posterior distribution, which is the conditional probability of the parameters P given the measurements Y, to the prior distribution and to the likelihood. The prior distribution is the statistical model of the information available about the parameters before the measurements are taken, while the likelihood is the statistical model of the measurement errors, which also represents the conditional probability of the measurements Y given the parameters P. The distribution appearing in the denominator of Bayes' theorem is called evidence, and it's actually a normalizing constant for the posterior. The computation of this of the evidence is difficult, so that many times Bayes' theorem is simply stated as the posterior being proportional to the prior multiplied by the likelihood. There are many situations in practice where the likelihood is not exactly known and cannot be approximated in terms of analytical distributions. There might also be situations in which the calculation of the actual likelihood demands large computational times and resources, thus requiring model reduction or data compression. While the approximation error model approach, which was developed by Yarikaipi and his colleagues, can be quite effective when a Gaussian distribution can be used for the total errors. And by total errors, I mean the measurement and modeling errors. This Gaussian model cannot be arbitrarily used in general. It's also important to note that data compression schemes like the ones quite popular nowadays, based on artificial intelligence, they might not result on an analytical likelihood. So the so-called approximation Bayesian computation, it can deal with measurement and total errors that may not be appropriately modeled in terms of an analytical distribution, or if the computation of the likelihood function is very time-consuming. We now come to the motivation for this work, which is related to the use of green materials for construction. Within the environmental context, bio-based materials have been increasingly used in building constructions due to their reduced ecological footprint and their thermal performance. Besides that, the properties of wood-based materials have a good reproducibility due to their industrial production. However, several recent studies pointed out the importance of accurately modeling the phenomena of water absorption in such materials to predict the phenomena of heat and mass transfer and to assess moisture disorders like mold growth. So the sorption curve is an essential feature for the modeling of heat and mass transfer in porous building materials. Several models have been proposed in the literature to represent the amount of moisture content in the material according to the water activity. And these models are based on analytical expressions and few parameters that need to be estimated by inverse analysis. Therefore, we come to the objective of this work, which was to select among 8 competing models, the one most appropriate to represent the measurements of water content in a wood fiber construction material during controlled sorption experiments. The model parameters were estimated simultaneously with the model selection by applying the ABC algorithm of Thon et al., which can be found in these references below. Although it can be claimed that the measurement errors in this work could be analytically modeled in order to be used for model selection and calibration, the authors have successfully used this algorithm for many applications, and then we have decided to go ahead and also use it for this work. About the experiment, this sample material was a wood fiber thermal insulator. It's commercially available under this name of PavaFlex Comfort from this supplier. It has a density of 50 kilograms per cubic meter and a thermal conductivity of 0.038 watt per meter Kelvin. Due to its low thermal conductivity, this bio-based material has been used as a building envelope, but it presents a strong hygroscopic behavior. So the sorption curves sorption curves were measured with 5 samples of this material by using a dynamic vapor sorption equipment, where the sample was placed in a chamber with controlled conditions of temperature and water activity. And during the experiment, the mass of the sample was continuously measured. And before the experiment, each sample was dried for 24 hours. The dry mass of the samples varied from 10.8 milligrams to 28.2 milligrams. Each sample was exposed to increasing water activity from 0.05 to 0.95 at a constant temperature of 23 centigrades. And the sample was maintained at each of these water activity levels until the moisture content in the sample reached equilibrium. The sample mass increased rate was carefully examined before moving to another activity level as a stopping criterion at each water activity step. This slide shows the equipment that was used for the experiment, as well as the variation of the sample's moisture content with the water activity. And for the 5 samples, and we can see that there is a good repeatability of the experiment, as we can even see with these zooms of the 5 curves, except for the very large water activity. The following 8 mathematical models were examined in this study. Actually, the model, they provide the moisture content U as a function F of the water activity A. And each model, it contains N parameters, and the parameters are represented by those P variables. And the domain of the water activity was limited to this interval between 0.05 and 0.95, because some of the models are not valid for A equals 0 or for A equal 1. So these are the mathematical models. This Brunauer Emmett-Teller model, it's given in this form. It has 2 parameters. The Guggenheim-Anderson-de Boers model has 3 parameters. Now the thermodynamic model, it also has 3 parameters, and it's given by this expression. The empirical Oswin model, then it has 2 parameters. The Fred-Long-Zing model, it has 4 parameters. The Wangen-Nushtens model, 3 parameters. And one additional parameter based on the literature was this one by Smith with 2 parameters. But this, we also proposed a new model in this work, and this was inspired by the shape of the sorption isotherm and its derivative, as compared to the tangent function. So the algorithm of Ton et al. For model selection, for simultaneous model selection and model calibration, I mean the estimation of the model parameters, is presented in this slide. And the objective here is to obtain the combined posterior distribution of the model and its parameters with the given measure data. In this algorithm, at the first iteration, a model is initially selected from its prior, and then a sample for the parameters of this model is obtained from its prior distribution, as illustrated here. This process of selecting the model and the sampling the parameters repeated until a pre-specified number of samples are accepted. And a user-selected distance function between measurements and estimated moisture content is used as the acceptance criterion instead of the likelihood. And this is done with a specified tolerance epsilon. And this tolerance epsilon, it varies at each population. The set of accepted, and by population, I mean the set of accepted samples. So new samples are generated by sampling the model from its prior and the parameters from their estimated distribution at the previous population. This process is repeated until the tolerance for the last population is satisfied. And as I mentioned, the tolerances are usually, they are reduced as the populations advance. They are usually set large for the first populations. And this is we do this in order to avoid lack of convergence when the sample is dominated by the prior. And as the information provided by the measurement becomes more and more significant as the populations advance, and then a large number of cells is selected for the correct model, and the samples for the parameters better reflect the real posterior distribution. Now we come to results and discussions. And before trying to estimate the parameters, we addressed the questions related to the identifiability for each model that was considered in the analysis. Since all models are simple and analytic, the structure of global identifiability was verified, thus shown for all models, thus specifying that a specific absorption curve could only be obtained with one single set of parameters, and this was verified for each model, as I mentioned. The sensitivity coefficients were also examined for each parameters, and the sensitivity coefficients are given by the first derivative of the model response. In this case, the moisture content with respect to each parameter, it's represented by the variable theta. And as an example, we present in this slide the sensitivity coefficients for the parameters of this GAB model. And since the parameter estimation problem is nonlinear, the analysis of the sensitivity coefficient is local. So these two figures, they show the sensitivity coefficients computed with two different sets of the model parameters. For both cases, we note that the sensitivity coefficients are not linearly dependent. And also, the magnitude of the sensitivity coefficient with respect to the parameter P3 is much smaller than those for the other parameters. Therefore, the moisture content for this model, or predicted with this model, is very little affected by this parameter. And unfortunately, its estimation with high accuracy is difficult in this case. The global sensitivity index that is obtained by the integration of the square of the sensitivity coefficient in the activity and parameter domains. It was also used to assess the sensitivity of the model of the moisture content with respect to each model of each parameter of each model. I'm sorry, as shown in this table. And we can, this global sensitivity index is actually a relative quantity. And we can see that it confirms the result that we have seen by the analysis of the sensitivity coefficients, which shows that the GAB model is very little affected by this parameter P3. Actually, this table shows that only these Smith's, which is the SM model, and the model proposed in this work, which is this MADS model, they are the only two that all parameters are equally, more or less equally affect the measured quantities. So for the implementation of the ABC algorithm of Ton et al., the distance function was taken as the Euclidean distance between estimated and measured moisture content. As I mentioned, the tolerance aimed at as the populations evolved, and we tried to satisfy Morozov's discrepancy principle at the final population. This variation of the tolerance as the populations evolved, it was selected by numerical experiments. And this was also the case for the number of populations, which was selected as 22, and also the number of particles, which was selected as 4,000. The perturbation kernel that is used to explore the parameter space at each population, it was chosen as a random walk move with an uniform distribution. And a maximum perturbation of 1% of the maximum parameter value was used for this kernel. But as I'm going to show in the presentation, that the results, they were not affected by this kernel. All models, they were assumed as equally probable, and the uniform priors were also given for all parameters. And the ranges for these priors, they were also obtained from numerical experiments and from literature values, so that the resultant moisture curves obtained from the models, they could encompass all the experimental results. So these are the uniform priors, and you see that for some of them, they actually are not very much informative, and they actually encompass a large variation of they include a large variation of the parameters. Okay, so this figure, it shows how the tolerance was varied as the populations evolved. These are the number of populations, and while this figure on the right, it shows the acceptance rate at each population. Okay, so we see that the acceptance rate, it decreases with the population, and this is because the tolerances were reduced. And also, we note here that the acceptance rate is strongly dependent on the size of the kernel that was used to search the parameter space. When this kernel was increased from 1% to 10%, we see a sharp decrease in the number of accepted in the acceptance rate. Because it's more difficult to improve the agreement of simulated and measured moisture contents with candidates generated with such a large kernel. This figure shows the model selection through the 22 populations, and this was for the kernel of 1%. And initially here, the 8 models, they have the same number of particles. But until population 4, there was no strong selection among these 8 models. However, at population 5, Smith's model was then less selected, since it did not succeed in representing the moisture for high water activity. And that at population 5, no particle satisfied this distance test, the distance test for this model with the candidate parameters. Thus, after population 4, Smith's model was no longer selected. And at population 9, it can be noticed that only 3 models were still competing. The model proposed in this work, this MADS model, the FX model, and also the GAB model. at the final population, only the MEDS model satisfied the distance test for the lowest tolerance. Although this was the only model selected from population 20 onwards, the last three populations, they were needed to correct the calibration of this model to better select to better estimate the parameters for this model. We also note that in this figure that the results, they were not significantly affected by changing the kernel to 10%. And at the final population, still the model proposed in this work was the only one accepted. It's also interesting to note that the dispersion of the samples of the parameters as the population evolved. So in this figure here, we can see this shows the increase in the population number. These are the parameters, and each dot here represents one of the samples of the parameters at each population. Okay, so as the populations advance, and the model better reflects the experimental data, so the variation of the parameters, it decreases. This can also be seen by this figure here, which shows the standard deviation of the samples of the parameters. And at the final iteration, we can actually obtain these approximate marginal posterior distributions for the two parameters of the MEDS model, which in fact they exhibit small variances. The accuracy of the selected model with the correspondent estimated parameters, it can also be assessed by comparing the model predictions with the measured data. As shown in this figure, in blue we have the experimental measurements, and in red here we have the simulation under uncertainty on the parameters. I mean that the parameters, they were sampled from their posterior distributions, from their simulated posterior distribution. And actually the moisture content predicted with this model and with the uncertainty in the parameters, they exhibit a small dispersion. And they also exhibit a good agreement with the experimental data, even for large water activities. Now some conclusions, and a new model was proposed for the sorption curve of a thermal insulation material made of wood fibers. And this model was inspired by the shape of the sorption curve in comparison to the tangent function and also its derivative. The ABC algorithm of Ton et al., it was used for simultaneous model selection and model calibration by considering 8 competing models. And the proposed model was the one selected. And actually, the approximate posterior distribution of the estimated parameters exhibited small variances. Similarly, the moisture content simulated with the selected model and with the approximate posterior distribution of the parameters had small variances. The CPU times, they were about 50 minutes for the kernel of 1% and 30 minutes for the kernel of 10%. The difference in computational time is due to the reduced acceptance rate for the kernel of 10%. But still, it's a small computational time, and these were obtained with a MATLAB code running in a computer with an i7 CPU and 30 GB of RAM. So this basically concludes my presentation, but let me make was the opportunity to make an announcement. Actually, this announcement was made about the same date last year in Agadir during Zurich 19. I'm organizing this 8th International Symposium on computational heat and mass transfer. The symposium is belongs to the series of conferences of the International Center for Heat and Mass Transfer. Unfortunately, we had to postpone the conference because of the pandemic. Had to take this decision in the worst occasion of the pandemic here in Brazil. The conference is going to be held next year in hybrid format with in-person and online presentations. And the one-page abstract is due December 18th. Okay. So finally, again, thank you very much, the organizers, Professor Gahum, Professor Lahus, Professor Zaz, Dr. Homani. Very great pleasure to be here. And I'd also like to acknowledge the support provided by agencies of the Brazilian government, and also the French colleagues want to acknowledge the Junior Chair Research Program from the University of Savoy-Mont Blanc, in collaboration with the French Atomic and Alternative Energy Center and the Scientific and Technical Center for Buildings. So this concludes my presentation, and thank you very much for your attention.
Thank you very much, Professor Aland, for this interesting presentation. And I'm just checking if there is some questions for the moment. You don't have any question, but we can still receive the questions along the conference. So I have one question, if you might. Okay. Mind about
no, absolutely. Shall we stop sharing here? I'm going to stop sharing.
Okay. So you talked about the CPU time calculation. What is interesting also. Yes.
Excuse me, the question just after presenting all.
If you want, no problem. Thank you.
Okay. Thank you.
I will introduce Professor Enrico Fabrizio, who is from Politecnico di Torino, and he is also a colleague. I know very well Professor Enrico Fabrizio, who is graduated from Politecnico Torino and in Lyon as PhD. His field of interest is performance simulation and optimization of zero energy buildings. He is very active at the level of International Energy Agency, and he participated to many annexes and programs, EBC and ECEC, especially namely. He also very active in editorial and publication domain. He serves as review for many international journals. And he is also associate as editor at the Sustainable Cities and Society Journal. He was, thanks to his efforts in this field, he was awarded by RIVA, awarded by the European Federation of Air Conditioning and Association. And he was within the teaching supervisors of CSUT at Politecnico. And now, today, Professor Enrico Fabrizio will talk about simulation based on optimization methods for zero energy buildings, design, insight, and beyond. The floor is yours, Professor.
Thank you, Mohamed, for your very kind introduction. Can you hear me well?
Yes, perfect.
Perfect, thank you. So I would also like to thank the scientific teams and the organizers, in particular the organizers of workshop number 4 for inviting me for this talk. Now, let me start from one question. Do we know what zero energy buildings are? Well, 20 years after its first introduction, the concept of zero energy building is now one of the main topics of any course on energy conscious design. There is a large literature, a large variety of building types and systems. And despite the differences that arise when we look at how zero energy building or nearly zero energy buildings as they are defined and in European literature in standard and legislative requirements around the world, you can see that in this table there is a variety of different points of definition implemented into each national EU legislation. But despite those differences, the ZEP target has been the driver of a large amount of research activities in the field of building energy performance. So from a theoretical objective to be defined and discussed, and who can ever forget the Torcellini's paper on zero energy building, zero cost building, zero emissions, etc. on 2006. So this has become a current construction practice, and there are reasons also to say that it has been the leading topic, especially in some European countries, in this specific building physics field. But if we are asked what is the recipe of a zero energy building, well, everyone knows the answer. That is the super insulation, obviously, the mechanical ventilation with heat recovery, the system efficiency, and the use of renewable sources. But is it as simple as that? Well, the recipe is far from being as trivial as it may appear, since previous studies demonstrated that the ZEP design that best suits a certain location will not necessarily be the optimal one for our location, and that the current design of a ZEP has to be resilient in the future, or has to be able to adapt to climate change. This is why, even though a considerable amount of research has been performed on ZEP, this topic is still of great interest for academics, for researchers, and also for the construction industry. So if we look at how the zero energy building is currently intended, we may summarize it as it is the sum of the most performing envelope, the most performing HVAC system, and the use of renewable sources. But it is not the result of a simple sum, because of the many interactions between the various design parameters and the boundary the constraints from the boundary conditions. We can say that the design of a zero energy building is a real complex optimization problem. Which type of optimization problem? Well, if we try to state this problem from the generic optimization problem, which reads, I have to minimize a certain function subject to some equality and inequality constraints, and to some constraints on the input parameters, if we customize, if we tailor this generic optimization problem to the problem of the design problem of ZEP, we can see that there are some decision parameters that concerns the use of energy from renewable sources, the systems, the envelope, the design. There can be many objective functions because they can be energy use, primary or energy delivered. They can be the cost, the comfort, and that there are a number of different constraints, which are, for example, the scenarios, but mainly the building energy model, which is the main constraints of this problem, highly constrained. So this summarizes the main feature of this type of optimization problem: the number of design variables, the type of design variable which are discrete, the number of objectives. And one way to solve and to address this problem, and it is the way I will concentrate from now on, is the so-called simulation-based optimization. So the coupling between, in the building physics field, between building simulation software and optimizers, external optimizer, which is not the exact result of this optimization problem, obviously, but it is a trade-off between complexity and accuracy, which is very interesting. So some features on this simulation-based optimization for the design. Everyone recognizes the impact that building simulation has on the design. Many new certified buildings has to be simulated following certain procedure and approaches, like the certification in sustainable buildings. But if we think about the optimization problem is as simple as it may appear, well, let's take this very simple case study, one single family building of 2 floors modeled into transit. This is a real building, but we consider it as an archetype building for optimizing this building type, in the sense that this is already a very energy efficient building, but we take it as a reference case study because there are also monitoring results, etc. So let's think of some optimization parameters. Let's think about 9 parameters that concern only the envelope of the system, like thermal resistance of some envelope components, like the window types, etc. They had the initial value, they had the maximum and minimum values, they have some steps, so there are different number of points. In the end, this optimization problem is a 9-dimension optimization problem, non-uniform 9-dimensional space search with this very large number of points. And if we assume to do the simulation like that, the total simulation time of the entire space would be 130 years, which is obviously not possible, even though the case study is so easy and so simple. So there are 2 ways. The first way may be to reduce the order of the problem, so to use reduced order problem and couple those reduced order models with optimizer or with some parametric designers. The second way is to couple the simulation with some heuristic optimization algorithm. So to use external optimizer coupled to the simulation engine. There is a variety of simulation-based optimization methods in the literature. You can find many framework. Each researcher is organizing his main framework. There are common couplings that I indicated here in the slides between Energy Plus or Transys, or generally a building simulation engine and an optimizer, and some post-processing or optimizer tool like MATLAB, like GenOp, etc. Well, let's see now a sort of multi-scale set of different applications of simulation-based optimization methods. I will not concentrate on input data and hypothesis. Which I would like to give you now is a sort of a picture of the many possibilities and the results that can be obtained by exploiting such methods. For each example, you will see also a sort of you will see a reference, so you can find and retrieve all the information you would like to know. Let's start from a very simple case, the case of an enclosure. Okay, this is just an enclosure. If you would like to design a school classroom, and the optimization parameters are the overhangs, the shading, the dimension of the windows, the colors, for example, of the external walls, the internal walls, the layers, the construction. So very simple design parameters. What we can obtain, we have to set out the optimization problem like that. So we have to pre-process all the input data and not only the boundary condition, but especially to size and to define the optimization input parameters and the various settings. Then these optimization input parameters are fed into an optimizer that is coupled with an energy model. The optimizer at each time iteration, at each simulation iterations, sets out the input parameter, then passed into the energy models, then an objective function is computed that is also able to drive the new try of the optimizer. There is also the need to have a post-processing in the sense that, for example, in this case study, we need also to consider not just the energy objective functions, but also some objective function, which is this one, but also some objective functions on the thermal comfort or on the daylighting index. So if we look at the results, we can represent a result like that. So on the bottom, you have the annual primary energy needs considering lighting, cooling, and heating, the summation of lighting, cooling, and heating, ordered from the largest to the lowest, from 110 to 80 kilowatt hour per square meter per year. The number of iteration, and so the number of different design solutions is larger than this one, 2,400, because this is the number of absolute solution. So maybe the optimization run takes 5,000 or 10,000 different iterations, but in the end, the unique design solution are those ones reported in this slide. On the top, you can see the trend of the order of the daylight factor and of the thermal discomfort index. The best way will be to be at this side of the diagram, where we have the lowest energy, the highest daylight index, and the lowest discomfort index. Each point of this diagram represents a quite different design solution. And in fact, we can see that, okay, and in fact, we can see that we have, I mean, there's just some problem, but it's not particularly important what we can see now. We have just to wait for the presentation to charge, I think. And it is more interesting to look at how there is the trade-off between energy, comfort, and the daylight index. So in the next slide, that it is going to appear, what we are going to see is that there is a bar diagram. Okay, that should be fine now. Okay, this one. There are some bar diagrams in which we represent all the variations into primary energy, the variation of the daylighting index, and the variation of the percentage of the outside range, so the thermal discomfort index. Each dashed line, this one, the small one, represent the minimum of primary energy, the minimum of the thermal discomfort, and the maximum of the daylighting. So the best, let's say, options. What it is quite evident is that we can see on this side and also on this side that for the different locations and orientation, these are just two different locations, one more cold and one a bit more hot in Italy, we can see that the optimal energy value, this black one, is always near the optimal thermal discomfort, because the green and the black are quite near also on the other side, while instead there is always a difference of 1 point of daylight index between the energy optimum and the daylighting optimum. So these types of analysis and of presentation of the results can be able to drive a good exploration of the design space. If we look then at what happens when we go at the building scale, these are examples from optimization of the envelope. It is the first problem I presented to you before, the one of the 130 years. How differently energy systems affect the optimal design of the envelope parameters. This is also quite interesting. We have two different climates, one which is a bit colder and one Marseille which is a bit warmer. We have these clouds of points. Each point represents a design solution, a unique design solution, and these clouds of points represent different energy systems. So I'm coupling some envelope design options with different energy systems. This one, for example, which has a larger consumption of kilowatt hour per square meter per year, is the one that exploits electricity. So if we look at the parameters, we can see that there is a variation, okay, between parameters that are okay. This is a variation on the envelope parameters, and in case of Marseille, parameters are more stable in the sense that varying the energy system does not really affect, for many parameters, the optimal design of the envelope. Instead, for the cold climate, there is a variation when we change also the energy system. So this means that if we use a sequential optimization, traditional sequential, instead of an integrated optimization, we can find different results. This is the comparison. It's another study that compares the results from integrated optimization, so energy supply and energy demand option at the same time, with a sequential optimization in terms of cost. Many design parameters changes when we look in an integrated fashion at optimizing building systems, building components, building envelope, etc. And also other examples can be found on the comparison between, I mean, it's a bit slow, this presentation, so I will have to go a bit quicker because time is flying. This is a presentation of the robustness of a solution. If we think of one optimization parameter that has a value, for example, this one, the red dotted one, and we think how stable, how robust is this parameter in the neighborhood of the optimal solution. So we are not just looking at the very optimal solution, but we are looking at the neighborhood of the results within the optimal one, the one that changes for plus or minus 3%, for example. So we can see that some parameters are quite stable in the sense that also in the neighborhood of the optimal solution, they assume the same values. Other parameters are not robust and should be not considered as optimal design values. Some applications can also be found on the trade-off between energy efficiency and use of renewable energy. This is, for example, the case of the trade-off between global cost, the cost for the energy and installations of a solar cooling system for a large multifamily buildings, and the relation between the percentage of renewable energy, the cost, and the primary energy consumption. Now, I would like to conclude presenting you the results of an application which comes from the Solar Decathlon China 2018. Well, the Solar Decathlon case study is interesting because it deals with the transition between design to construction and operation of a building. It proved that it was possible to reach the zero target, but special attention should be paid to the transition from the stage to the design to the following one. Within the large work that there is around a solar decathlon competition, I would like to present here the work we did to optimize the prototype of the building, considering variables related to the design and variables related to the operation of the same building, exploiting the capabilities of simulation-based optimization method. It was a unique opportunity to apply in practice this context. I think that most of you are familiar with the solar decathlon context. So it is an international competition on the design, construction, and operation of a very innovative, very energy efficient small house, residential house, which is only powered by solar energy. Teams are composed by engineering and architecture students, which are tutored by faculty advisors. And I was within one of the faculty advisors responsible for the energy engineering topics of one student team, which was a joint student team between South China University of Technology and Politecnico di Torino. The house was built 2 times, a first time in Guangzhou, then was disassembled and rebuilt in Dezhou. Now, this is just a picture of the real building once it was constructed into the context side. We wanted to win the competition, so we tried some ways to increase the contest rules. We considered the contest rule, which are based on 10 contests for a total of 1,000 points. Each contest has 100 points. Some contents are defined by juries. So there are some analysis of the document, interview, exhibitions. Other contents are based on measured and task performance. We concentrate on the measured one. So we try to express into an objective function the solar decathlon contest rules. And to do that, we have to know which are the penalty functions for the observation. So the observation in terms of temperature, relative humidity, CO2 levels, etc., that for the 14 days of the contest are recorded by third party, and they are used to complete the contest point. There are some penalty. For example, you can see for the temperature that you have to be within the 22 and 25. Instead, you reduce your pointer, or you do not gain any point if you are too low or too above. Similarly for relative humidity and also CO2 level, PM2, and for the energy use. Okay, so the energy use, if you are a positive energy, you gain the whole amount of point. Instead, you reduce your points. So in the end, we built an objective function which has 180 points. This is the setup of the optimization. So first, we had a reliable and calibrated building energy model, because the building was a first time built in Guangzhou. Then the setup of the simulation-based optimization, and then the results were used for tuning the final design, and especially for during the operation of the final contest stage. This is how it is settled up the simulation-based optimization problem. It is quite similar to the previous one. I would like to add that the contest period is 14 days, and the time step of the simulation we adopted was 1 minute, because we had to simulate accurately the performance of the system. The optimization parameters are related, are this one with the values in the initial and final values. They are related to both the envelope construction, what may be able to change between construction 1 and final construction in the context side, the use of shading, fixed and movable shading, the tilt of the PV array, which may be adjusted, the set point of the systems, because this was very important, the set point, and also the time of operation, the operation of movable shading control, And finally, also the ventilation controls, the time on and off. In the end, we, from the result, from the numerical result, we gain 170 points up to 9%. This is the final result. So we had to slightly adjust with the lower insulation and higher mass the envelope to be used differently the shadings, to change the time of turning on and off the ventilation systems, and to change a bit the set point temperature. And the final result was that also due to this operational optimization, the prototype won the first prize, the first prize of the competition. It won the first prize also in the engineering contest, in the innovation context, and in the other contexts. So the simulation-based optimization was really able to drive to a better design and operation. To conclude, I would like to point out some aspects. The first one is that simulation-based optimization methods are really able to turn the traditional sequential approach to an integrated one that considers both options from the demand side and the supply side together, which is very important, as I think I have demonstrated. This is also a powerful tool for the industry to demonstrate the impact of the technology or the market penetration of some new technologies. Since each study on zero energy projects has to be intrinsically holistic to capture the complexity, at least the use of simulation-based optimization model is able to catch this behavior. And finally, well, something I presented today may seem quite academic, quite scholarly today, but this will really have an impact on industry and on building construction on a short term, some years, as the lessons learned from the solar decathlon in China can testify. Let me thank you for your attention. There are a number of references, and also I would like to thank all my research team members for their support during this work. Many, many thanks to all the listeners and the organizers.
Thank you very much, Professor Fabrizio. I have some questions for Professor Holland and also Professor Fabrizio. But please, it is already mentioned yesterday by Professor Fabrizio, just only use the Q&R for only questions, because I received a kind of people asking for internship or something like this for professors. You can even contact them directly. I guess if they have some opportunities, they will be happy to share this with you. So for Professor Holland, there is a question about the fiber orientation. Is fiber orientation important in the case of your study? If yes, has it been taken into account and how?
Well, good morning again. Thanks for the question. And if the interest is to work on the PhD with me, you may contact me directly, please. Please feel free to do this. About the question, I would say that for this case, the orientation was not important. As I understand, the experiments were done with small samples, and actually, it's a lumped model. So it's all surfaces of the samples, they are exposed to the same water activity, and what we are measuring, the moisture content, it's also global within the sample. And in fact, since the experiments, they were done with 5 different samples with different masses, and we don't see an effect. Okay, I'm not saying that the orientation of fibers would not be important for properties like the thermal conductivity or diffusivity, but for this experiment in special, they were not.
Okay, thank you. And there is also a question about the number of iteration, because you mentioned the time. There is, I will make, yes.
Okay, yeah, this algorithm, you have to turn the buttons, you know, you have to tune the algorithm by doing numerical experiments, and that's what we did. So we now have experience with this algorithm by applying it for different applications, like even for hyperthermia treatment of cancer. So different applications, and usually around 20, like 30 populations or iterations are enough. But the success of the algorithm, it depends strongly on how you vary the tolerance for that distance function that is used to examine the convergence for each population. And this is also where it's kind of tricky, but you have to do some numerical experiments.
Okay, thank you. And last question is coming from me. So, you know, is there any way to have a reduced model? Because if we want to couple it in a large scale, for example, is there any efforts made by you or your team to establish a reduced one faster to be coupled to a large scale, for example?
Yeah, actually, all those models, they are very simple because they are analytic expressions. They are algebraic expressions. But, but you're right. No, in this business, when you do inverse analysis within the Bayesian framework, especially when you try to do those stochastic simulation, to use those stochastic simulation algorithms, it's very important to use reduced models, because the computational time may be very large. And there are some very good approaches to consider not only the experimental errors in the calculations, you know, in the solution of the inverse problem, but actually the total error. Now that accounts also for the modeling error. So you can have like a complete high fidelity model and propose the simple model, a low fidelity model, and you still take into account the errors between the models. In this low fidelity model, it's interesting because it can even be meta model. You know, like many people today use artificial intelligence tools, neural networks, this kind of stuff, you know, POD to represent this low fidelity, this reduced model. But this still can be, the error between the models can still be taken into account in inverse analysis within the Bayesian framework, formally and very elegantly.
Okay, thank you.
Excuse me, please. I have a question for Prof. Orlando. It is possible, please.
Yes, yes. You can just have to raise your hand, and then you can.
Okay.
You can. Yeah.
Okay. Thank you very much. I am Professor Mohamed Garoum from École Supérieure de Technologie du Salé. Hello to everybody, dear colleagues. My question is for all models presented by Professor Orlando. Some models with only 2 parameters, and I ask if it is possible to use only the classical methods like Bayes gradient methods algorithm to estimate the parameters in place of the Bayesian approach. Thank you.
Yeah, nice to see you.
Hello. Fine. Thank you very much.
Yeah, you're right. No, any algorithm could be used. The idea behind this work was to simultaneously select the model and calibrate this model by estimating the parameters of the model. So you actually end up at the end, you know, at the end of the day, you get the best model with the best parameters that represent the experimental data. That was the idea of this work. Okay. There are other techniques that do not require that may require more strict assumptions like the analytic and likelihoods within the Bayesian framework. But we have been so successful in using this algorithm other times that we simply went ahead and applied this. I mean, this approximate Bayesian computation algorithm. But you're right. For this measure of parameters of one single model, you could be using classical methods. There are only a few parameters.
I think there is a microphone who is still open, and we have a kind of surrounding discussion that is polluting this, this discussion. If you can turn off your, if you are not speaking, you have to turn off your microphone. Okay, there is, thank you, Professor Orland. And
thank you.
For Professor Fabrizio, I have a question, because very interesting the question of zero energy building and the concept paradigm. And also the fact that you mentioned this solar decathlon competition is the real way to test and to assess in my idea, the performance. But I paid attention to the criteria you have, especially for humidity. You are still scoring 100 points, even if the humidity is less than certain amount. And I think if we have very dry environment, it's not comfortable. For temperature, you have a kind of triangle. But
you are completely right, Mohamed. These were the rules of solar decathlon, but you have to think of the fact that we were in summer in China with 34 degrees and 60 or 70% relative humidity outside. So the problem was dehumidify. So I think that they defined these penalty rules because of the problem is to dehumidify and not the vice versa. But you are obviously completely right, for sure. Yes. Thank you.
Thank you very much. It was very interesting, and I am still waiting for questions. There is one question for Professor Ibrahim Ben Hamou from Marrakesh. How you calculated the correlation of the measured temperature, slide 19, as the points on the graph are very dispersed. The question is how you calculated the correlation of the measured temperature in slide 19.
Okay, yes, of course. In this figure, I can see that the correlation coefficient is not very high. I don't remember the right number. It's around the point, maybe 0.7. But this is not the most important thing. The most important thing is at this depth, 1.6 meter, the temperature oscillation is still, it's not stable. Temperature is not stable. So there is some oscillation of temperature. This is why there's this dispersion. So when we represent, I haven't time to present all the results, but representing time variation of the underground temperature at this depth, 1.6 meter, and the temperature of the slab on ground surface, you can see that this is the best matching between these temperature. This is the best depth for this temperature matching.
Okay.
So that's why I concluded that the temperature of the slab and grade of the monitored building is around the temperature of the ground at 1.6 meter. So just to remind the motivation of this study, because in Morocco, in Marrakesh region, with hot climate, hot and continental climate, the thermal regulation imposes thermal insulation of the slab on grade, which is completely aberrant.
Yes,
so
yes.
This
I agree with you.
Study was to say that this is completely aberrant to impose this, even in Rashidia. It is imposed in Rashidia. It is not in Casablanca. It should be in Casablanca. It should be in Agadir. It should be in Tangier, but in Marrakesh region, in Rashidia region, in the desert region, no. In Ifran, yes. In Ifran, it should be. But in Marrakesh, in the hot climate, the ground is the friend of the building.
I agree with you. I agree with you. But insulating the floor in this region is not logical. So thank you very much for mentioning this. We are very, very tight in time. So I have one question which disappeared from Mrs. Larossi. It has been, wait, this is one question for Professor Larossi. Which parameter should be considered to construct a heat material able to store the energy in order to use it in solar drying outright? So I think the question is, the person is wondering about the parameters.
I think that's the material having a great capacity, great value of capacity and energy.
D'accord, energy, so and capacity.
Okay.
Yeah, yeah.
Thank you.
I think it joins the same remark as Professor Ibrahim. Thank you very much, professors, for this very interesting.
Sorry, Mohamed. If we can have just one quick question.
Yes. Yeah,
Professor Fabrizio. I
think
it is very
you are very welcome. You are very welcome. You can go.
Yeah. Okay. This is a comment to Professor Fabrizio. I think the paradigm of net zero building, or even the zero building, or even the positive energy building, is not really the best way to achieve the sustainability in buildings, because as you mentioned, in the solar decathlon competition, you can achieve a positive energy building, but your building is not sustainable at all, because you can use active systems to achieve this. You can use storage, you can use batteries, you can use a lot of non-sustainable elements to achieve this. So this is the first comment, and the second comment is about the comfort model. You know, when you do simulations, you use softwares, and these softwares, there is a comfort model. And in most of the software simulation for buildings, transit, or maybe in energy, I know transit. In transit, the comfort model is a deterministic one. It is a finger one, such as the finger. It is not really it is not really the best model to achieve sustainability. The adaptive model is most adapted to this. Thank you.
Well, I would say that there is still room to define a new objective function that is able to, express the degree of sustainability of your new design, in the sense that simulation-based objective method can change the design variables. So we are waiting for someone who is doing also what you are going to propose for the sustainability, for the evaluation of the sustainability. Also because there are many international protocols on sustainability which are based on different quantitative, qualitative requirements. So the problem will be to implement them into a building optimization scheme. And the second one, I mean, in our case for solar decathlon, we decided to use let's say a Fanger model, since the building was there was a complete control of the HVAC on the ventilation. But obviously, when there is no complete, fully mechanically control, the model of the adaptive comfort should be preferred and can be easily integrated into software tools. Now, also models that are able to model the behavior of the users, in the sense how many times they do open the windows, etc. are connected to the building simulations. I'm thinking about the research of Mohamed, for example, no? And other researchers around the world. So it can not only be as deterministic as in some cases.
Okay, thank you very much. We don't have to forget neither that this solar decathlon, it has its own standards and specifications. So we have also to meet them. Yes, this is when we are studying a completely controlled building and we have active systems. I think Fanger is the best one. But when we are in free cooling or natural ventilation, I think also that adaptive approach are sweet. So thank you very much for this very interesting presentations and discussion. Now we'll go forward to the short presentations. I have the first one is I think I also have the control. I will say yes. So the first one is I'm trying to is about a study of SWH system, individual and collective configuration under ETC and FPC technologies, presented by Mr. or Mrs. Garab.
Please go to the next slide.
Yes, I am trying to click on the next slide, but it's not. Yes, yeah. Okay, so presented by Mrs. Fatima Zahra Gargab, then from Sidi Mohamed bin Abdullah University, Fes from Morocco. So there is a kind of delay between my actions and what is happening on Zoom. It's running, but I think we don't have the sound.
Present work is a study of solar water heater in Morocco. This work will be organized as follows, presenting all objective simulation models and also
We'll lose the presentation. So if you can just try again to, yes.
Present work is a study of solar water heater in Morocco. This work will be organized as follows, presenting all objective simulation models and also all results, technical, economic, and also the payback time. This study aims to compare different configuration, individual and collective, and also two technologies, the ETC and the FPC, under different payback systems such as gas and electric. Simulations were carried out for specific demand of 37.5 liters per person for a building of 16 apartments. We have here the simulation models for collective and individual systems. First, the energy demand was calculated for two cases. In general, the results are very satisfying and approximatively similar for FPC and ATC, with small positive difference for ATC. These identical results, explained by the collector area difference, FPC are slightly greater. Some temperature decreases are explained by the thermal losses in tank and piping, while important temperature in individual tanks explained by inertia effects heat stored since previous days. For two technologies, an analysis of the solar fraction and energies provided concludes that the ETC are more efficient on all Moroccan cold zones 4, 5, and 6. For zones 1 and 2 characterized by their moderate climate, we note that the two technologies are identical during the year, except winter, when ETC is the best. The energy savings calculation requires different hypotheses showed here. So here we have the calculation of conventional system annual energy. So from the graphic, we can note the influence of the system efficiencies and also the influence of the cold water temperatures on the energy demand. And here we have a total energy demand of the building using the electric water heater and the gas water heater. It found that the gas water heater systems increase the total consumption of the building. So the energy saving rate was calculated taking into account the electric water heater as conventional reference system, replaced by all studied system ATC and FPC with different backup system electric and gas. All choices can save about 50% of global energy as an average, but the evacuated tube collector using the electric backup is the best. So here we have the energy savings evaluation, but here using the gas water heater as a system of reference. So we have the same results approximately. The evacuated tube collector using the electric backup is the best, but the savings are more significant than the previous system studied. The economic savings were calculated in the real data. So solar water heater solutions instead an electrical system for demand of hot water production as a reference save between 46 and 75% of the energy bill. For the gas as a reference and considering the subsidies of the gas applied by governments, the saving is modest, about 20% as an average. In contrast, without the governmental subsidies applied on gas, we can exceed 50% as an average on the energy bills for the both technologies. The solution is useless in terms of investment for gas system. If the gas prices are without subsidies, it will be highly attractive, while it's feasible in the case of conventional electric system. As a conclusion, we can say that all configurations are feasible in Morocco, replacing the electric conventional systems. But for gas, the subsidies block those solutions. The individual is better talking about the payback time with a small difference, but the collective still the best for a good energy management. The results are remarkable in the hot climate in Morocco, but still very good for all other conditions previously presented. The ETC is more efficient, but in favorable climate and hot climate, the two technologies present a good performances satisfying the needs.
Thank you very much, Fatima Zahra. And now we will go through the presentation of Mrs. Nisrin Lagmish from the University of Abdelmalek Saadi of Tangier in Morocco. And the topic is about numerical analysis to assess the indoor temperature distribution in large building by an integrated thermo-hydraulic zonal approach. And also thank you for the assistance for the
PhD student at the Faculty of Sciences and Techniques in Tangier, Morocco. What I'll be talking to you about is a numerical analysis to assess the indoor temperature distribution in large buildings by an integrated thermo-hydraulic zonal approach. So we are all aware that in the last decades, the population is becoming more and more demanding and aware of the need to ensure a comfortable living or working environment. In order
think there is a sound problem, so the presentation. Yeah, if you can, yeah. Thank you very much for this assistance, yes.
To ensure this, the thermal study is no longer sufficient, either for engineering or for scientific research, which always aims to develop an explicit methodologies that can be used to approach the reality of the buildings without any experimentation. So the order of the presentation is as follows. First of all, I will be looking at the problematic and objectives. Then I will move on to methodology. Thirdly, I will discuss some of the obtained results. And finally, the conclusion. So the key issue of this study is the large buildings. According to Annex 26 of the International Energy Agency, it is considered large if one or more of the statements apply. For example, the occupied area should be small relative to the total value. In this kind of building, the notion of the indoor temperature variation within large buildings induces the notion of vertical stratification and/or horizontal temperature distribution. In order to accurately calculate stratified air conditioning load, it is particularly important to predict indoor thermal environments. This later can be predicted by two approaches, CFD, numerical approach, and zonal models. However, the application of CFD models remains limited in the engineering domain because of its computational time. However, the zonal model is considered as an intermediate approach between single zone and CFD models because the zonal method requires fewer zone division than CFD approach and provides sufficiently detailed results. This work, entitled Numerical Analysis to Assess the Indoor Temperature Distribution in Large Building by an Integrated Thermoaerotic Zonal Approach, is developed to respond to all of these types of constraints. In particular, for example, to reduce the computational time for modeling the temperature distribution by CFD approaches. Now we pass to methodology. This research consists in performing thermoaerotic zonal model using a coupling of transits and quantum. As shown in this figure, the indoor space is decomposed into subzones accordingly to horizontal and vertical directions. For the horizontal subdivision, three kinds of subzones are existed: corner, middle, and center subzones. This figure shows the example of the center subzone. To apply this methodology, we have chosen a building with these dimensions, and it is located in a city that is characterized by a hot Mediterranean climate. Now we pass to results and discussions. So now we will present one of the results obtained in the vertical stratification. A comparative study was conducted to evaluate the effects of occupancy and on the vertical gradient of temperature. As a result, we evaluate the impact of occupancy rate on the vertical thermal stratification. As we can see in right figure that the increase in indoor temperature caused by the number of occupants induces a variation in the transition zone. This phenomenon can be explained by the stack effect. Total temperature distribution, a combination with natural light ventilation and international gains, has been evaluated. So a maximum difference temperature between the opposite subzones is about 3 degrees Celsius. It can be noted that the natural light ventilation is not sufficient to ensure acceptable indoor thermal conditions. To sum up what I've just said, that the advantages of the integrated thermoaerotic zonal model developed in this study are shown in this slide in 5 points.
Hello everyone, my name is Elias Abdounou and today I'm very happy to present my project Untitled Modeling and Control Framework for Energy Sharing on a microgrid solar automata approach. So as you see in this picture, 110 trillion US dollar is the investment by 2050 to achieve energy transformation, namely in renewable energy and energy efficiency. Normally, two factors behind this transformation. The first one is the commitment of government to implement energy efficiency programs and repent of climatic change, and second one is drastic reduction of renewable energy costs. For example, between 2010 and 2019, solar photovoltaic fell 82%, and this normally motivates people to use renewable sources to produce their own electricity, and that's what we call consumers become prosumers. But still some problem related to exploitation of that at a small scale for generation. The first one is the intermittent nature of renewable generation, and second is limited participation of consumers in energy market. So the concept of peer-to-peer energy sharing can offer a possible solution of that problem. The idea is very simple, is to connect several households and then they can exchange energy between each other. Our objective is to give a modeling and control framework for managed supply and demand decision, but this time using solar automata approach. What is solar automata? Solar automata is a discrete system in which space, time, and state are discrete. They can be defined by the equation 2-1 plus boundary and initial condition. Finally, we can say that the solar automata is a mutual interaction between cells governed by simple local rules. That means we start from simple local rules and then we can model a complex and dynamic system. The question now is how we can implement or applicate a solar automata for energy management. Actually, this figure gives an answer for that question. They present the proposed approach of energy management in a microgrid, and actually is divided in two parts. In the first one, we run the solar automata to define the sender and the receive address, and also the value and the price of the transfer. And then we validate the transaction using blockchain technology. Now, let me describe the model. The lattice is the microgrid structure composed of households connected to each other via the grid or power interface, and the state corresponds to the energy statue of household, and we have defined 5 states: demand satisfied plus demand satisfied minus surplus power deficit, and grid connection. So the statue of a cell at the moment T is written via this configuration, and we can say that the state of a cell is a combination of 3 parameters: the amount of energy generated by renewable way, the consumed by load and stored, and the batteries. We can of course compute the 3 parameters using equation 3.4, 3.5, and 3.6, and to validate our model we have used the collected data of Solar Decathlon Middle East 2019. This is the figure of the solar village of Solar Decathlon Middle East. And for simulation condition, we consider 15 houses is the houses participate in the competition. Time step 30 minutes for 1 day of simulation. That means 24 hours. Initial condition, we suppose that all the batteries are full charged in the beginning of simulation, and for state connotation we consider this color to represent the state, and for the input of our model we consider the PV production of each house, demand profile, the grid excess injection, and grid consumption. Okay, this is the simulation result, and we can say that it's divided into 3 parts. The first one is from iteration 0 to 18. Supply and demand is well balanced. There is no exchange of energy between neighborhoods. It's normal because there is not any solar radiation. And the second part, from iteration 20 to 24, solar automata is in action. Neighborhood with excess energy automatically exchange the requested energy to balance the energy flow. And the last part is from 6 p.m. to 11 p.m. Energy exchange is stopped at 7 p.m. due to the lack of solar radiation. That's all. Thank you for your attention.
Okay, thank you, Mr. Abdnur Elias from the University of Abdel Saadi of Tangier. Sorry, I have my microphone which was off, and I didn't have time to. I didn't pay attention that it was off, so I introduced Mr. Abdnur. So he's from Tangier, and as you remarked, he talked about modeling and control framework for energy sharing in microgrid cellular automata approach. Thank you very much for your presentation. And now we have to move forward for Khalifa Salhi from Algeria. And the topic, Mr. Khalifa's topic is numerical evaluation of a heat pump with coaxial heat exchanger for cooling and heating of an office building in the Algerian climates. The floor is yours.
Hello, I'm Salhi Khalifa, researcher in Renewable Energy Center, Algeria. I want to participate in ERSEC 2020 by this article entitled Numerical Evolution of a Heat Pump with a Coaxial Heat Exchanger for Cooling and Heating of an Office Building. This article is a part of the National Renewable Energy Program in Algeria. This program aims to reduce fossil energy consumption by 30% up to the year 2030, broken down by sectors as follows. The Renewable Energy Center in Algeria tried to share in this goal. The Solar and Geothermal Energy Division is responsible of this part of the. She proposed a project in Renewable Energy Development Center in the Ben Aknoun city. This project is a heat pump coupled by office building and coaxial heat exchanger. The main objective of the project is to analyze the performance of coaxial heat exchanger at a depth between 15 and 30 meters for soil condition and the Algerian climate. Firstly, calculation of the soil temperature as a function of the depth in Algeria. Mathematical models of different designs of coaxial heat exchanger for geothermal heat pump. Performance analysis of a coaxial heat exchanger with different configurations and comparison with conventional heat. Coaxial heat exchanger model's design is presented in Figure 1. An inner pipe is placed inside a large outer pipe forming an annular cross-section between them. Grout and groundwater fills the space between the outer pipe and the bare hole walls. Circulating fluid can enter the heat exchanger through the inner pipe or annulars and flow downward. The fluid travels upward through the outer results and discussion. The building's air conditioning needs were calculated using the Energy Plus program. Figure 2 shows the monthly average air conditioning load. It should be noted that the cooling season runs from May to September. As we have seen, the cooling energy needs reach their maximum in July. After a one-dimensional modeling with MATLAB, the best results are as in the table 1. The results are for the whole heat exchanger. The figure presents the temperature distribution along the inner and outer tube in the coaxial heat exchanger. The temperature of the water increases with depth along the ring gradually at the beginning and quickly after. Before peaking at the bottom of the wall, the maximum bottom water temperature decreases from 37 to 14 during the 1 year's simulation. The water in the production tube, after being heated in the ring, consequently loses heat to the water injected in the ring. The temperature of the produced water decreases from 35 to 31 during the simulation. Figure 4 shows the estimated daily performance of the system during of July and to August. The COP results obtained show a rather stable performance of the operation of the system, and the COP of the heat pump was relatively higher than the whole system. The system COP values have also changed dramatically over time. Such fluctuation can be caused by the high energy demand of building in timely manner. The important results are presented in the discussion. The project is under construction, and next year there will be experimental results. And thank you for your attention.
Thank you very much, Mr. Khalifa, for this presentation. And now the next presenter is Said Ali Farhatia from University of Msila, Algeria. And the topic is DC microgrid energy management system for commercial building comparative studies. The floor is yours.
The presentation of our research entitled Energy Management System for Commercial Buildings. This research is realized by Farhatia Said Ali from University of Msila, Algeria, and the research team from University of Nantes, France. This research firstly presents the problematic of the proposed topic, then a discussion of the building power system architecture is realized. Then we will see the studied energy management systems after the construction of the models under MATLAB. A simulation is carried out and the results are discussed. This paper ends with a conclusion. As it's known, the buildings are consuming a very significant amount of energy from the distribution grid. This imposes a technical and economical challenges concerning the reliability of the grid and the price of electricity. To meet with these challenges, a local renewable energy source such as solar photovoltaic array, a backup system including fuel cell and a battery are proposed. This power grid is composed of photovoltaic array, solid oxide fuel cell system, a battery bank, and the main grid connection system. However, the interaction between these sources may occur several challenges. For this reason, the energy management system has been designed to meet the following objectives. First, satisfy the load using the local produced energy, including the photovoltaic energy or the fuel cell energy. Then, reduce the fuel consumption and the operating cost as possible. Restrict the power source degradation, especially the fuel cell, which is very sensible to the fluctuation in the power. And last, ensure the stability requirement for the system. In the literature, mainly there is two major categories of energy management systems. The first are rule-based energy management system, and the other is the optimization-based energy management systems. The most used for energy management strategies are the fuzzy approach, the equivalent consumption minimization strategy, and the external energy maximization strategy. These three strategies are used as a comparative study in this study. Concerning the fuzzy approach, as you know, fuzzy logic controller is used where the inputs are the net power, P loads, PPV, and the other input is the state of charge of the battery. The output is the power reference of the fuel cell. And the strategy is the equivalent consumption minimization strategy. The goal of this strategy is to minimize the overall consumption of the fuel by minimizing the fuel cell consumption and the battery equivalent consumption. This objective function is submitted to some constraints such as the state of charge and the fuel cell power. This system will generate the fuel cell power reference, and the DC bus voltage is stabilized using the battery power as shown in this figure. The last strategy in this study is the external energy maximization strategy, which aims to maximize the given objective function. This objective function is related to the battery power and the DC bus capacitive power. By maximizing its power, the overall consumption by the fuel cell will be reduced. This objective function is also submitted to some constraints. The overall control scheme is proposed in this figure, where always the DC bus voltage is regulated by the battery power. Mainly, this grid is operating in off-grid mode. However, if the battery state of charge is upper than maximum level or lower than its minimum level, the grid will turn it on grid mode, and the battery will exchange its power with the main grid, depending on its state of charge, to prevent it from the deep discharge or the overcharge. As depicted in these results, the battery will share much power using the fuzzy logic control over the other techniques. However, in the total cost operating, the external energy maximization strategy provides better performance. Regarding to the lifespan of the battery, the external energy operates the battery in its allowable range better than the other techniques. Second scenario, no fluctuations in the output PV power, and the battery will see it in first of the day charging, and the second part will discharge depending on the net power required by the load. As shown in these results, the same performance is given as the first scenario, where the optimal choice is always given by the external energy maximization strategy. As a conclusion, the external energy maximization strategy can provide the best performance comparing to the other studied strategies. However, the obtained performance by the fuzzy logic controller can be improved by optimizing its scaling factors or its membership functions. This can be done in our future works.
Thank you very much, Said Ali, for this presentation. So we have to go forward for the second, which is from Mr. Abdel Ali Rahmouni from the Faculty of Science of Dar al-Mahraz, University Sidi Mohamed bin Abdullah from Fez, and the topic is microstructural characterization of calcareous stone by thermal conductivity scanning. Floor is yours.
Dear colleagues, my work is focused on microstructural characterization of calcareous stones by thermal conductivity scanning. In this presentation, I will start with an introduction. Subsequently, I will talk about the materials and methods, then the results of my work, finally a conclusion. Many materials, natural and artificial, are heterogeneous and porous, saturated or unsaturated with fluids. The study of thermal behavior of these materials is fundamental for many applications such as civil engineering, geophysics, and historical monuments. The objective of this work, measurement of thermal property using TCS, characterize the porous network, porosity, heterogeneity, and anisotropy of calcareous stones. The materials studied in this work are calcareous stones used in construction of historical monument of Morocco. The calcareous stone is sedimentary rock. It is characterized by high and variable porosity, and chemical composition is very rich in calcium carbonate. Measurement of thermal conductivity are performed on 6 samples in direction X, Y, and Z. The measuring process is based on the optical scanning method developed by Prof. It is characterized by non-descriptive measurement of thermal properties. We impose a unidirectional heat flow on the sample and measure the temperature difference across the sample. The thermal conductivity of the sample is calculated by this equation. The variation of thermal conductivity as a function of position is shown for our calculated sample in dry and saturated states. In dry states, the thermal conductivity is strong along the anisotropic planes X and Y direction. It is weak in the perpendicular direction Z. In saturated states, the thermal conductivity is greater along the perpendicular direction. Charlie and Rebash proposes an estimate of porosity using this equation. The variation of porosity from this equation is shown in this figure. The porosity is greater in perpendicular direction, which shows low thermal conductivity in dry states and high thermal conductivity in saturated states. Conclusion. The thermal conductivity scanning analysis allows definition of relationships between porosity and thermal conductivity at the millimeter scale. Measurement of thermal conductivity allows access to the porosity on one side of calcareous stamp. The calcareous stone is characterized by a strongly heterogeneous structure. Thank you.
Thank you very much for the presentation. And the next presentation also comes from the same department as previous. The presenter is Mohamed Ali Haj Ammar from Algeria, and from the Hamma Al-Khadar University. The topic is numerical study of solar cooling system with novel activated carbon methanol pair. The floor is yours.
Hello everyone, my name is Mohamed Ali, University of Al-Wad, Algeria. The presentation today in International Conference on Renewable Energy under topic numerical study of solar cooling system with a novel activated carbon methanol pair. Our work presented the performance and absorption cooling system driven by solar energy, so you have a study according to the following problem. The consumption of electrical energy has increased in recent years, especially in Sahara region for cooling production. As well, the use of CFC and HCFC in cooling systems has become air pollution. Therefore, using renewable energy has become a hot topic, so the present work introduces a study of solar absorption cooling system. A question: what is solar absorption cooling system? As illustrated in the figure, the system uses a pair of activated carbon methanol integrated in a solar collector, in which the generation of the methanol during the daytime in the solar collector and its production during the night. So the aim of the study is this: to find, according to the operating condition, the suitable working pair for best system performance. In the following, the system thermodynamic modeling is based on the Benau-Strakov state equation, isosteric heat, input heat, cooling production. And to evaluate the performance of the system, two parameters were selected: the system COP, which is calculated, and daily S production is given in kilogram. As illustrated in the table, the proposed thermodynamic model of the system has been validated. Accordingly, it is found that the system performance of 0.68 and a total daily S production is 1116 kilogram. As well, the advantages of the system compared to no solar cooling system are the electrical daily saving and avoiding CO2 emission. Moreover, the illustrated in the figure and table, the activated carbon based on stone coal should be chosen rather than another activated carbon tubes for system performance. From the simulation result of the system, it was a conclusion that the optimal performance was equal to 0.73 with a total daily S production of 3065 kg using the activated carbopoison on stone coal associated with methanol as the refrigerant. Thank you all.
Thank you very much for the presentation. And now we'll go through the last presentation given by Mr. Hamadou Diop from Thiès University of Senegal. And the topic is the use of soil TIFA materials to So sorry for this inconvenience. So it's technology. The topic I said is the use of soil TIFA materials to enhance local material and improve the energy efficiency of building in tropical area. Thank you, Mr. Hamadou, for launching the presentation.
Hello, ladies and gentlemen. Welcome. My name is Ahmadou Diop, and I am a PhD student in Laboratory of Materials and Energetics in University Institute of Technology in Thiès, Senegal. Today, I want to go to share with you my work titled Use of Soil TIFA Materials to Enhance Local Materials and to Improve the Energy Efficiency in buildings in tropical area. And by doing this work, I want to go to share with you the following content. I will start with an introduction, and I will talk about the material and method that I have used for characterization, and I will talk about how do I have to make formulation of the samples, and after the result and discussion. To remember you, Diamniadio is a town located in about 35 kilometers from Senegal's capital, and this town is taken right now to be the new town of Senegal because it has as objective to decongest Senegal's capital. But the main problem of this region is its soil is very rich in clay. And the other problem is we have found in Senegal a vegetable called Tifa australis. And this vegetable has some thermal properties, which is very important, as you can see in figure 2. And in figure 1, you can see the soil collected from Diamniadio. And the following picture show you the area occupied by the Tifa australis in Senegal. As you can see, all green colors shows you that the area where we can find the Tifa australis. So it is very present in north of Senegal than the rest of the country. That's the reason why also right now Senegalese government and Mauritania government have working to a same plan for finding solution to fight against the proliferation of these plants. And as you can see always here in this photo, to show how does the Tifa is growing in area where people are practicing rice culture. And this is very dangerous for this population because right now they are going to lose their lands. And for doing this job, I have used many types of materials as cathode apparatus to have an idea about the index of plasticity and the sieve particle analysis and the press and asymmetrical hot plant, as you can see here in this photo. And for the formulation, I have made two types of formulation. The first one is parallelepiped samples for characterization of thermal properties, and the cylindrical samples for mechanical characterization. And the proportion that I have used for its formulation is also described in this paragraph. And I have used the three materials. The first formulation is only built by Tifa and by only soil of Diamniadio and water as a reference formulation to have an idea about all properties, thermal properties and mechanical properties of the soil alone. And the second and the third formulation are built by using Tifa australis, soil of Diamniadio and water with a right proportion, as you can see in the paragraph. And after this formulation, I have found the following result. The first one is the shrinkage rate. As you can see here, for soil of Diamniadio alone, you can see about 29.19%, but it is decreasing when we add again Tifa australis. And the atomic limit also is shown by this curve, and it is equal to 20.47. That means the soil of Diamniadio is plastic. And as a result is the density of the composite materials. For Tifa, for soil alone, we can see the density is very high. And if we add Tifa australis, the density is also decreasing. And also this same phenomenon is seen for thermal conductivities. When we add again Tifa australis, the thermal conductivity also will be decreased. And here, for example, we have represent a curve talking about the superposition of thermal and mechanical resistance. As you can see also, the thermal resistance is going to be increased when we add again Tifa, but the mechanical resistance is going to be decreased. So we have to find an equilibrium between thermal resistance and the mechanical resistance for building materials with a high property of energy efficiency. So, ladies and gentlemen, this is all that I have to share with you for this presentation. And if you have any question, you can contact me directly. It was very, very a good project for me. Thank you very much.
Thank you very much, Mohamed, for this presentation, and thanks all the participants to this workshop. Very nice presentation and keynotes. In Q&R section, I have for the moment only one question dedicated to Mr. Khalifa Saleh from Algeria. And Mr. Rosha asked if you can answer. He would like to ask what was the refrigerant considered in your study. Can give the if you can give the floor to Mr. Khalifa to answer the question.
Yes, hello.
Yes.
Yes, the refrigerant in this system is the water,
okay.
And the refrigerant is in the heat pump is the R4010A.
Okay.
In the heat pump.
Okay,
Yes.
thank you very much for answering this section. Is there any other question from the attendee or who would like to ask our presenters any other question?
Yes.
Yeah.
Yes.
Go ahead.
Yes. Yes. In fact, I have. These are not questions. These are comments on the papers ID 453 and 455. For the first comment on the presentation given by Mrs. Gergeb from FAS, I think comparing solar water heater to electric water heater, of course, solar water heater is competitive. But in Morocco, this is not the most used system to heat water. The most used system is gas. The most used fuel is gas to heat water in homes, in houses. So from an economic point of view, comparing solar water heater to a gas water heater, the first one is not competitive. The solar water is not competitive at all. Even if we don't take into account the government subsidies, it's not at all. So the solution is that the government have to subsidize such solar water heater because this system prevents importing gas from abroad.
I think Mrs. Fatim Zahra is raising her hand, and probably she can clarify the context and why she used this configuration.
Yes, first, thank you for giving me the opportunity to present my work. So first of all, I want to add that this study is in the context of national projects, which is Shamsi projects, is a collaboration between Lyon and University Sidi Mohamed bin Abdullah. The goal is to have national products, solar water heater made in Morocco. So for that, we carried out a lot of studies, which are strategical and also the technical study based on research and science. So this study is in the context of strategical studies. So in my study, I take into account the several scenarios that exist. So now we have the electric and we have the gas. I treated in my study the two scenarios, when we have the gas and when we have the electric, and the benefit that can bring.
No, you can go ahead. It's just someone who was speaking without.
Okay, thank you.
Yeah, you can go ahead. Yeah.
So I said that we try to study all scenarios and all cases that exist now. So we have the electric and we have the gas and the benefit that can bring. We did a lot of other studies, such as the generalization of solar water heater in Morocco. And when you talk about generalization, we talk about replacing all systems that exist, and we talk about electric also. So in the two cases, we have benefits, and we studied all technical, economic, and also the payback time of all figures that exist to have a complete study. Thank you.
Thank you for answering this question. Thank you very much. Any other questions? You can. Yes, you can.
Can I go ahead for the second comment? Just a suggestion for this, for Mrs. Gergab. I think that you should perform an economic study taking into account the price of the gas as it is imported from abroad. You should have this, you should include this in your study to perform a global economic study to show to the government that if the government did not subsidize the solar water heater at any scale, it will not work at all. Okay, for the second comment on the paper ID 455 by Mr. Elias from Tangier. I think the project that is proposing is very interesting, but exchanging energy, electric energy between houses in the Moroccan context, it is not a realistic project at all. Because indeed, in the frame of the renewable energy law, it was amended in 2016, when you put energy, net energy in the grid, the producer is not selling energy to the utility. You can get back this energy, but if you don't get back it yourself, it is lost. It is lost. Yeah. Yes. And you cannot sell it for another house.
But I think, Mr. Mohamed, they are performing some researches independently on the current constraints. So it could be very interesting. I will give first the floor to Mr. Elias Abdenour to react, and then I will answer. You can answer, Mr. Mohamed. Go ahead, Mr. Abdenour. Yes. You have the. We can't hear you. Mr. Abdenour Elias, you rise. Okay. Yeah, go ahead. Talk. Yeah, you can talk. Yeah.
Maybe he has a problem with his mic.
Yes, I think.
Despite the fact that that he is turning it on.
So I can continue my my idea. Yes, I agree with you, Professor Mohamed, that it's not feasible for the moment to sell the energy, and if you produce more than you need, it is lost, and sometimes it's more expensive to store it and to reuse it. But I think in this kind of research, they are futurist research, and they can be, in my idea, very, very useful if the regulation standard and the context and the Moroccan context change in the future. So this is why it's a kind of research, in my idea, very interesting. If we change the paradigm, the Moroccan paradigm. So let's say if the near future, the situation changed, I think this study will be very, very interesting in Morocco. Of course, at the moment there is some regulation constraints. You can speak, Mr. Abdullah. Yeah, you have the floor. Mr. Al-Hibawi, if you can give him the control, or I think he raised his hand, but we can't hear him. Has some microphone problems, I guess. Anyway, you can write in the discussion your idea, Mr. Abdullah, so that I can we can see it. Yeah, this is the big problem of some studies, because we always think that they are not adapted. Yeah.
Sorry, just an additional comment. There is an ongoing modification of the regulation for renewables in Morocco, and the ongoing modification is the net metering. There is no, you cannot sold electric energy, but you can store it.
You can store it, and it's very expensive to be stored. But my idea is that this kind of studies could really reorient the regulation. If we
I agree.
We can use rather than be completely barriered or stopped by the regulation. I think that this study could be used and analyzed by the stakeholders in order to reorient the regulation and give this opportunity. I agree with you. It's a kind of it's at this moment I agree with you, but it's very interesting if the next regulations, because storing energy is really very expensive. Otherwise, we can also use some DC equipments in building, directly use the DC heat pumps and other equipments in the buildings. Unfortunately, Mr. Abdul, we can't hear you. If you can try again, because you deserve to react. You can talk. I say that your microphone is on, but we can't hear you. Anyway, there is a technical problem. Yes.
Can I have another question for the last presenter? The last presenter, Mr. Ahmadou Diop. Just a clarification about the component of the bricks. There is soil and there is these fibers, and there should be something other to stabilize the blocks. What is used to stabilize
thank you,
the block?
thank you. Do you have me?
Yes, right, yeah.
Okay, thank you very much for your question. I think the problem is in Senegal, in this area, we found some materials which are rich in clay. And the problem of this clay is that they are very unstable. That is the reason why we combine the clay with the Tifa australis and also the water with a right proportion, in massive proportion. And after the stabilization will be given by the presence of Tifa, because in Tifa is a vegetables which we have found some fiber, and the fibers are able to increase the stability of the material that we'll have at last. I don't know if you hear me.
Yeah, that's okay. Okay, thank you very much. It's clear.
Okay. So you have also the floor for you, Mr. Benhamo, if you have additional questions and even we can give some time for other presenters if they have to, if they need to add something for their presentations, some words, or to ask other presenters.
We can give the floor to attendees if they need to ask questions or live questions.
Yes, if you have some questions for the attendees, I'm still.
Please raise your hand.
Yeah.
Hello.
Yes. Yeah.
Hello. Sorry. Just one additional comment on. I don't know if Professor Fabrizio is still here.
I think he is Fabrizio. No, but if you want, you can.
Okay, just because in his presentation, talking about zero energy building, he talked about super insulation.
Yes.
I'm not sure that super insulation is the let's say the unique way to achieve zero energy building. In some climates, super insulation may lead to an additional consumption, an additional load, such as in Morocco. Most areas in Morocco are hot climates. So when you use super insulation, when you insulate, especially the walls, and these this is not just. These are my affirmation is based on our research since 2012 in most of the Moroccan climate, except for Ifram, which is a cold climate. When you use, and maybe in Tangier, Tangier also, it's somewhat cold. When you use super insulation, you get overheating.
Yes, I agree with you, but
and nowadays, even in Europe, you have for overheating problem with the climate change.
Exactly.
So I think thermal inertia may be used in this case instead of insulation. Thermal inertia may stabilize high mass walls, may stabilize the indoor temperature.
Yeah, you're right, because in hot and mid climates, super insulation is very, let's say, dangerous, but could be interesting in very cold climates like Scandinavian and other cold climates could be interesting. It's like triple glazing or something like this for insulation. You're right, but under Moroccan or Mediterranean, let's say, climates, super insulation in my idea also is not very very needed, and it could be even harmful for the performance of building, because as you mentioned, it can lead to summer incomfort, overheating, and so on. I have a remark. It's fundamentally necessary to have methodology and techniques to offer as alternative, both traditional and modern, and especially local solution. You are talking about which presentation, Mrs. Raja Al-Khmeri? You can have can raise your hand, and then you can develop your idea. Yeah, you can speak. Can you please give the floor to Mrs. Raja Al-Khmeri? She raised her hand.
She has the floor.
Yeah, but you can activate your microphone. Please activate your microphone. Activate your microphone. It's off. Your microphone for the moment is off.
Thank you. I said about the main of presentation of this afternoon. We encourage students to have many ideas and to have as likely bibliothèque, you know, as a solution for every situations. Not only in phase or in Tangier. You know, you can modify conditions and apply your solution for another town in other countries. So it means you know, in globality, you know, that was my comment for
Yes,
this
yes,
presentation.
I can understand your comments. So we shouldn't focus only on one city or one climate. We should to keep
Because
yeah.
he thought about phase.
Yes.
Ifren, he described about stones, but if you have some ideas, some studies, it will be made like art
Yes.
for progressing, you know.
Yes. I agree with you. So yeah, I am also very convinced that every solution, every technology, or every technique should be discussed and studied under several climates and location, not only focus on one or two. But I think it's just an example. So if you have a technique or a solution or a contribution, it should be discussed under several climates to see if it is adapted or no, and completely agree with you. Yes. So any other question or remark? And I noticed that this workshop is very wide, and there is a lot of techniques, envelope characterizations, systems.
Okay.
Yeah.
Thank you very much, Professor Mohamed Mankibi, and thank you very much for all participants.
Thank you again for this workshop, which is very. I think I suggest that all the participants continue discussing and innovating after this workshop. And the workshop here, the idea is to launch a kind of discussion and to gather people and to make connection. And then you can, I think that all the presenters have left their contacts, and you can directly contact them. And thank you also for all the conferencier and the attendee for animating and enriching this workshop. Thank you also, Mr. Youssef, for organizing, and also for the assistance. And
thank you.
Without the assistance, this workshop normally will not be well held. It's a success. Thank you very much.